groups have access to those files. So the management capability across is really easy, intuitive, and easy to navigate and manage. The system allows for quick upload and download of data files, and then the rendering of the visual files. If you put a file in, for example, that's a GeoTIFF, and it may not have a correct projection or something like that, and you try to render the file, the system will come back to you and tell you, sorry, I can't render this file because the projection is not right, or something to that effect. You can make those corrections, or if you have a question for us, our help can help you do that. But in general, it's very intuitive, and once you've done it once or twice, then you're pretty well at it. So then you have a great way to manage your survey data, to organize your viewable and your non-viewable files, and to include anybody that you want to in terms of participation in those files. So to summarize, the idea of Absolute Ocean is to provide a tool that allows us to build survey projects for an entire team that they can access, view, share, and analyze, as well as grow and keep. And the nice thing about cloud-based systems is they have a very, very, very long memory, so these things can stay there for as long as people are able to access it through Absolute Ocean and then beyond through other access methods. It includes both visual and supporting data files. We allow people to do all kinds of adding, changing, deleting the project information in near real time. As quickly as you can get to an internet access and load those files, they can become visual. Seriously, we have done surveys where we have gathered side scan data, processed that side scan data on a small vessel, been within cellular range of an internet connection, uploaded GeoTIFF files, and made them viewable to the customer in a matter of minutes. So it happens that way. Easy access for all your stakeholders, suppliers, project managers, engineers, regulators, analysts, the public, as well as professionals. Easy access to the file systems. There's no client software required in order to use Absolute Ocean. And finally, big point, you don't have to ship any data around. No sticks, no drives, no PDFs. It's all in Absolute Ocean. So that's what we're doing. I appreciate your time. Thanks.
Ken. I was monitoring Slido, I didn't see anything come in. You're going to be giving a demo this afternoon.
Yeah.
A little more interactive. So if there's questions, as I'm sure there will be, we'll address those this afternoon. We're going to move right on. I think we have Colleen Peters is next. Is that right? From Saildrone. And we're going to roll out data.
It's just a visualization.
Hello everyone, thank you for joining me. My name is Colleen Peters and I am the Bathymetry Data Manager at Saildrone. Today I'd like to talk to you about what it's been like to map the seafloor remotely with wind power. First I want to give a brief overview of the company. We are headquartered in Alameda, California, which is where the majority of the platforms are manufactured, assembled, and tested prior to engaging in missions. Then we just opened 3 new offices this year in St. Petersburg, Florida, Washington, D.C., and Fall River, Massachusetts. We have 3 main business lines: maritime domain awareness, which is mostly engaged with military and government applications for intelligence, surveillance, law enforcement. We have ocean data, which has been around for a number of years, and is really the basis of the Saildrone design. That is used for measuring surface, sea surface, and atmospheric measurements with a wide variety of sensors, typically customized by the mission team. And then we have our third line, which is added most recently, ocean mapping, which of course I will focus on today. We worked with a wide variety of partners, from government to industry to academia, and the list keeps growing as more and more folks want to engage with remote operations. Today I want to focus even more tightly on the most recent mission, which is Aleutians Uncrewed Ocean Exploration. This project was funded by the Ocean Exploration Cooperative Institute, and in collaboration with all of the partners listed, They all participated to decide on the areas of priority interest to be surveyed. The surveyor has a number of sonar systems installed, but our focus on this mission was the use of the Kongsberg EM304 and EM2040 multi-beam sonars. As the surveyor is 72 feet long and 14 tons in weight, it's a little bit more challenging to ship closer to the working area, so the surveyor had to make the transit first under its own power. So we started in Alameda, California, pictured on the right-hand side of the map, and transited over to Dutch Harbor, Alaska, where it was then deployed to start the mission. The operating area then being around the Aleutian Islands. You can see on this figure, I have the GMRT, JEPCO, and NOAA, NCEI mosaics displayed with the polygons that represent the survey areas on top in yellow. And this really captures very easily, very simply, the fact that Alaska is one of the least mapped areas of the USEZ, and hence why it was chosen to support this project, to try to add to the existing mapping data in that region. It was also a great area to be used for our first survey mission because the region is very hard to get to. There are not so many ships that operate in this area, and the weather window to operate in this area is relatively small. Harsh conditions start in the early fall, go all the way through the end of the spring, so it really only leaves a couple of months of the year to be somewhat comfortable to operate in. So this was a really great test for the endurance of the vehicle and its ability to work in this difficult environment. In addition to the mapping, we also had installed the MBARI environmental sample processor, which was used to filter the water from the sea surface to collect eDNA throughout the course of the mission. So in order to conduct mapping operations, we have a staff of pilots that will watch over the vehicles and take care of their navigational safety. And they are monitoring the vehicles throughout the entire Saildrone fleet, not just the surveyor. So some missions may have even multiple vehicles in one mission, and they are doing this over a 24-hour period in rotation between pilots in the UK, US, and Australia. For our mapping launch standards, however, we're all based in the United States and all log into the systems remotely. So we have a professional surveyor on duty 24 hours a day to make sure that the mapping systems are running, that they're using the correct settings, changing the line plans, and keeping everyone informed as to our progress. Taking a look at the areas to be surveyed a little bit more closely, there is a real scattering of data in different resolutions of different types of systems. And so the objective here was to be able to provide new high-resolution data for analysis. Now, one of the most interesting things about mapping with a sailing platform is that we can't really map or mow the lawn like we would on a traditional platform. Long lines, parallel, evenly spaced, parallel with the contours of the seafloor. That's just not how we're going to be able to work in order to really utilize the wind effectively. So we need to break down the survey into smaller sections so that we can continuously adapt to the shifting conditions, rotating the line plan orientation to accommodate the new wind direction. So the way that this works is that pilots will inform the survey team what the forecast is for what wind direction and what wind speed and for what period of time, and then the surveyor will build a line plan right in our mission portal to support that time frame. So not necessarily building a line plan based on a spatial measurement, but rather time. So a line plan that, say, might run for 12 hours or 24 hours in a particular direction. So this allows us to make the most use of the sailing capability, which then really increases our endurance. So in the event that we have light wind conditions or strong tidal currents, For a strong sea condition, we might have to engage the diesel engine that's on board, which is partially why we have it. We need to charge the batteries because multi-beam systems are a much bigger power draw than the sensors commonly installed on the Explorers. So we will, while sailing, only run the engine to charge the batteries, but then we can also engage the engine for propulsion if needed. So at the point, say, when the wind is less than, giving us a speed over ground of less than 2 knots, we might just start engaging the engine for propulsion to keep the pace of the survey moving. So the objective here on this particular mission was to sail as much as possible. And this is really made possible because of our ability to quickly adapt the line plans, thanks to a lot of the efforts brought forth by our software team. So for the surveyors on duty, monitoring the systems, the mechanisms you saw is the use of the near real-time coverage layer in our mission portal, which shows us the mapping data and most notably measuring the overlap and making sure that we have the appropriate amount of line spacing. Then we also produce daily mission products, which are manually created in Chimera on board the vehicle. Then they are automatically transferred and ingested into our mission portal. So not only our surveyors can see the previously mapped areas, but also our customers can see the ongoing progress of the survey. One of the unique capabilities of the surveyor is that we are able to conduct in situ sound velocity profiles. In our previous configuration, we had a profiler that was required to take off the vehicle in order to charge it, and this would be a real hindrance to our offshore endurance. So we made a really big and very important upgrade to the AML6, which has an inductive charger. So when the profiler is in the housing, it will continuously charge throughout the course of the mission, no longer impacting the endurance of the vehicle. So while we're mapping in the deep water areas, we're aiming for 2 profiles per day, and in shallow areas, which we consider to be less than 300 meters, we would aim for 4 profiles per day. Anytime that we were not able to collect any profiles, we would supplement with the World Ocean Atlas 2018 version from Soundspeed Manager. So in our mission portal, you can also see the geographic location of each of the profiles, as well as the metadata and profile data. So all of our surveyors could monitor the quality of those profiles as well as our partner. As I mentioned, we also collected DNA samples, and Chris Preston from Envari was kind enough to manually input those samples for the entire team to visualize in our mission portal. So you see the purple square is the start of the sample, and the water is filtered over a period of time, so that period of time is drawn out as a geographic path along the track of the vehicle. We had a couple instances of some storms passing through the area, and as they tended to pass on the Bering side of the ocean chain, we had to hide out on the lee side or Gulf side of the oceans for just a very short period of time. And this was a really sort of great testament to the vehicle's capability to keep mapping through some very adverse conditions. So having sailed in the area myself on the NOAA ship Oscar Dyson, I can tell you it is very uncomfortable most of the time. And while we had some conditions that did not allow us to conduct sound velocity profiles because the sea conditions were too strong and we could not risk the safety of the vehicle in deploying and recovering a profiling instrument, we were able to keep mapping. So we were able to keep going in the area with sustained wind speeds in excess of 50 knots, with gusts over 60, and significant wave heights of 8.1 meters. Now, 25 knots is a great sailing breeze to do some mapping, so that is a really great condition for the surveyor. So the sea state is really more of a consideration in terms of safety, because as you progress from one main survey line to the next, you may have to tack or jibe and going down, dead downwind is not the best direction for the vehicle, and through these different evolutions, we can experience some pretty heavy rolls of the vehicle, which is our biggest safety concern. So this was a really great opportunity to test the ability of the surveyor to continue mapping in some very harsh conditions. So the following figures are very preliminary. These are lightly or if at all processed data. So this is an overview of the entire mission thus far, where we filled in several of the survey areas and then collected data as well during transit. We went into port one time in the middle of the 51 days on the way and were able to exchange the eDNA samples so that way we could collect as many samples in the region as possible throughout the survey. The vehicle is on its way back to Alameda, California, and then we are going to go back out off the coast of the U.S. to continue the second half of this mission. So looking on the left-hand figure, you have a sort of before view of the area where you have the JEPCO grid behind the polygon. So on the top, of course, is our C4 bathymetry and underneath our C4 backscatter. So these figures, as I mentioned, are very, very lightly, if at all, processed. This is a real testament to how clean our data is coming out of the Kongsberg systems. So this is the only area that we surveyed with the EM 2040. It took about 6 days to cover 380 square kilometers. The Yamaha Pass was very challenging. We had a lot of tidal current issues, particularly in the northeast region, really just pushed the boat around. So that was a little bit of a struggle to keep line and fill in the polygon well. So some of the areas around this survey were a bit challenging and time consuming to try to fill in all of the gaps as possible. We had a bit of the same issue over here on the east of Siglong Island, but we persevered and were able to successfully finish the polygon. The Amalaya Basin area was a little bit easier after we learned some of those lessons in the Manuka Pass region. We were able to plan lines a little bit more efficiently. We had a little bit deeper area here, the bottom of the basin being around 1,000 meters. We had a little bit wider line spacing, which is really more the kind of depth that EM304 was designed for. Just want to leave you with a couple of images from the field. The bottom two are really what it looks like most of the time out there, but the top two images are the kinds of days that remind you why you like going to sea in the first place. So I want to thank you all for joining me today, and I hope you enjoy the remainder of the presentations.
David? Yep. You're going to join David Sandwell from Scripps is here. And are you giving a presentation or are we rolling video?
Presentation.
Great.
And how many minutes?
Like, an hour?
10? No, 10. Okay.
That was a great presentation by Colleen. I was really sorry I couldn't meet her here because that's a wonderful instrument they have out there mapping. So today I'm going to talk about the base layer of the JEPCO map and what we're doing to improve that base layer. Here's the people that have been working on it recently. Why don't I go to the next slide? The right of control. Or buttons. The red one? Okay, so I'll talk a little bit about constructing the base layer, what's new for 2023 data sets that we've assembled and so on. Talk about a little bit about mapping of uncharted seamounts for NGA and using scale and relevant capabilities, and then asking the question to you people, what's the most important thing for the next year of development? Okay, this is a busy slide, and I'm not going to go through all this, but just to give you a flavor of how the base layer is developed, we start with whatever we have in terms of topography, land topography that's out there, and then we assemble some ocean model. It doesn't matter which ocean model because we're going to perturb it using data. And then we add things like the Antarctic base map, FedMap 2. In the Arctic, we rely on the CAL version 3. And then the next step is to populate all the ocean data with predicted depth based on a combination of existing soundings and satellite gravity. And that changes periodically because the gravity field gets better, and I'll talk about that in a minute. Then there's something called SynBath that I won't talk about so much. It's more of an experimental thing that's really used by the physical oceanography community because it has more realistic seafloor slopes in the gaps, and these are used to generate internal waves and realistic currents and so on. Oops. Turn it back on. Okay. Not one slide, I'm not very good at this. Okay. So SynBath I won't talk about except for the seamount part of it, which is something that NGA is interested in. And then what we do after we fill in a prediction is then we add all the bathymetry that we have assembled. It's not everything in the JetCo grid, some stuff that first polishing it at 1 minute with single beam data. Single beam data are actually quite important in a lot of areas, but they don't look very good when they're assembled at full resolution. And then we polish it again with multi-beam data at 15 arc seconds, and then we plot the land on top of that and create a grid. And there's a SID, source identification number grid, like the TID grid, but it goes all the way back. You can drill all the way back to the original soundings that were used in that grid set. Just some things we're planning for the next one. We've added, we have new altimetry, and I'll talk about that in a minute. Satellite gravity, bed machine, trying to tune up the Antarctic margin. I know there's an Antarctic group doing that as well, but we're doing it because it's out there. We have new cruises from NCEI. We have a lot of cruises from BODC, and Pauline has, I should have mentioned early on that Pauline Weatherall is really working quite closely with us to provide updates of single beam data, but also editing the data has been a challenge and a lot of work, and she's been sending us polygons of bad areas that we then strip out of the base map. Go back. Oh, and then we're going to replace the Hawaii grid, and we have some sail-grown data that we're going to add. So a little bit about the latest gravity grids that are used to make the prediction. This is really moving quickly. We have new data from Cryosat. Cryosat's actually been operational since 2010. We have another one called Altica. We have data from Jason 1 and Jason 2. There's something called SWAT. It's a NASA SWAT altimeter that will be launched in December, and that might improve the gravity field even more. So the accuracy of the gravity field is constantly improving, and the resolution will never really get that better because it depends on the mean ocean depth. You're never going to resolve anything smaller than the mean ocean depth. But we can now start seeing all the seamounts. All seamounts greater than about 700 meters tall. And so here's a couple maps of seamounts that were digitized by Julie Dvorshian and as for her master's thesis. And this is an update of the Kim and Wessel seamount catalog. It's up to about 43,000 seamounts. All these seamounts are greater than 700 meters tall. Most of them are in about 1,000 meter tall range. And so what we do is I'll describe it in the next slide. We use a typical seamount shape, if there is a typical seamount shape, but we take the height to radius value that's typical of these 800 well-surveyed seamounts, and then apply that to these uncharted seamounts in areas where we have no data to get a realistic shape of the seamount. Rather than something very smooth, it comes out sharpened, it's a Gaussian shaped sharpened seamount, and every seamount has the same shape, it's very artificial, but it's something that the physical oceanography community is really interested in. So here's an example, these little bumps in the vertical gravity gradient are all seamounts that are now visible above the noise and the gravity. And so you can pick the locations of the crest of the seamount. That can be done to an accuracy of about 1 kilometer. And then we're going to model each one of these seamounts a little Gaussian in order to match the vertical gravity gradient that we have. And also the mean ocean depth. So here are the ship soundings in the area. You can see a number of seamounts that were surveyed, but there's also a lot that are missing. In the next slide, it shows the seamounts that are in the gaps. And then here's the old predicted depth based on just the gravity. And the seamounts are in there, but they're very subdued, they're blurry. And by adding the this information about the shapes of the seamounts, we get more realistic looking Gaussian seamounts. I don't know how to go backwards here. Is there a button here for backwards? Left? Okay. Okay, so, the right, oh, I see, I've been pressing the button, sorry. There we go. So there's the sharpening of the seamounts. And one thing about this sharpening is that they also improve the summit depth estimates. From the gravity predicted summit depths are all too deep, by about 500 meters on average. And so this is bringing the summit depths back closer to the real value. And this is something that we're working with MGA on because they're interested in hazards to navigation and so on. So now we can characterize these much better. And so there's, out of that list, there's 12,000 that are partially charted, 27,000 seamounts that are uncharted, there's 572 that have depths less than, predicted depths less than 400 meters. The error bar on this is like 500 meters. So it could be 0, it could be 1,000 meters. These are pretty much unknown. And then in the South China Sea, they were interested in that, we found 27 that were shallow. Now I want to transition into what MGA